Hey everybody, I'm going to use this video to go over the light and energy videos, E equals h nu, C equals nu lambda, and E equals hc over lambda. And I think the best way to go about doing these sorts of videos that have math and practice problems is to try it yourself. So I would watch me do the first video or do the first question, and then there's 4 questions in this particular video, and then the second one, read the question, pause the video, do as much as you can, unpause, and take advantage of that. Okay, so let's get started and do a little bit of math. So when we're using the formulas, the idea here is that we can convert frequencies and wavelengths and energies in between each other, and we can figure out what the frequency, wavelength, energy is of something. Okay, and so here we have a radio wave. Okay, and we know that because it says right there, this is ESPN radio. Okay, and it gives us kilohertz, and so it has recently moved to 610 kilohertz on the AM dial. Okay, and then the question asks for the wavelength. So here's how I would set these problems up so that you can get the right answer. Okay, I would write what you're given in the problem. Okay, you're given a frequency nu that equals 610 kilohertz. Okay, and then we are trying to determine wavelength. That's the question. Okay, and so which of the formulas relates frequency to wavelength? Okay, the formulas, and I'll just write 2 of them. There's E equals h nu, and then there's C equals nu lambda. So which one of these formulas shows the relationship between frequency and wavelength? And it's this one. Okay, I call this Mary's formula. Mary had a little lamb, right? See the nu lambda. Okay, I know, cheesy, but that's what I call it. Okay, so this is the formula that has both lambda and nu in it. And so I've written what I know, and now I'm going to take this and I'm going to put the formula here. Okay, now the other thing that we need to have is C. C is a constant. Okay, and it's always 3 times 10 to the 8th meters per second. Okay, and so now we can do, now we actually really don't need to worry about reading the problem. Now we can just solve the problem. Now the first thing that we should do here is convert this, because here we have kilohertz. We want to get it from kilohertz to just regular hertz. So we need to make sure, and this is true anytime you're doing a math problem, whether it's light and energy or whether it's stoichiometry or whatever it is, you want to make sure that the units are correct before you can before you move on. And so we want to go from kilohertz to just regular hertz in order to make sure our math works out. So down here, I'm going to go 610 kilohertz. Okay, and I'm going to X-line it. In order to convert, we're going to do an X-line. And so we want to go from kilohertz to regular hertz. And for every 1 kilohertz, it's 1,000 hertz. And so we multiply this by 1,000. Now I'm going to pull up my calculator. Okay, I think it's important to see this, so we're going to go 610 times 1,000. Okay, and now we can divide it by 1 if you wanted to. Okay, but that doesn't change the value, because when we divide by 1, it stays the same. So this is going to be 610,000 hertz. Okay, now remember that hertz can also be 1 over seconds, okay, just for future reference. But this is what we're going to do. So now all we need to do is, now that we have the right unit, and this is always going to be in the right unit. Okay, now we can just, what I call, plug and chug. So we're going to go 3 times 10 to the 8th equals frequency, which we have to use this frequency here, 610,000 over, or times lambda. Now to solve for wavelength, we have to get wavelength alone. So we're going to take and divide both sides by 610,000. Okay, now it may be insulting some of your intelligences, but you never know. Okay, some people may need to have that. Okay, may need to see that you have to divide both sides. So when you do that, you get lambda equals, and now here's what I also wanted to show you, is in your calculator, you're going to use the exponent button. And on a TI, let me show you where that exponent button is. Okay, and so if you look above the 7 here, okay, see it says EE right there? That is the exponent button. That right there. That's going to give you the times 10 to this. So when we do this, okay, what I'm going to do is I'm going to do this, and that gives us an E. That E, even though it's going to write 3E8, what that means is 3 times 10 to the 8th. Okay, so 3E8. Now, when we write our answers, well, I'll show you in later problems. Okay, so that's why I wrote that. Okay, is because that represents scientific notation, and that's how we do that in the calculator. So now I'm going to divide that by 610. Okay, and now our answer is, okay, our wavelength is 490, because we have to worry about sig figs. This is a constant. Constant has infinite sig figs, and so our measured value is this guy, and this has 2, so our answer has to be 2. And now wavelength, what's the unit of wavelength? The unit of wavelength is meters. Okay, so I'm sorry that this kind of got in the way. I thought that I had a little bit of room here. And so now our answer here is 490 meters. Now think about that. 490 meters. That is a half of a kilometer. That's one wave is a half of a kilometer long. That's pretty big wavelength. Okay. Okay, so I know that I went through that one fairly slowly. Let's do the next one, and let's see if we can do this a little more quickly. Okay, so we are given a wavelength of 589. Okay, so lambda equals 589 nanometers, and we want to know what the frequency is. Frequency equals question mark. Okay, nu. Okay, well, which of the formulas, E equals H nu or C equals nu lambda, relates wavelength and frequency? Same one. Okay, great. So we need C. So over here, I'm going to write C equals nu lambda, Mary's formula. It's not actually called Mary's formula, that's just me. And so C is 3 times 10 to the 8th. Okay, so now we plug in. Oh, before we plug in, we better check units. Okay, well, this is the constant, correct units, but now this is in nanometers. So we have to convert that. Okay, so I'm going to do that down here. So 5, oh, is that hard to see? I'll do it in black. 589 nanometers. We're going to X-line it, and we want to go from nanometers on the bottom, meters on the top. So every 1 meter is equal to 10 to the minus, let's see, I did that backwards. Okay, see, I can make mistakes. Every 1 nanometer is equal to 10 to the minus 9 meters, and that's 1 times 10 to the minus 9 meters. Okay, So when we do this in the calculator, I'm going to go 589. Then I'm going to go times, because I'm multiplying. That's what this is. Nanometers cancel, giving us meters. Okay. And then I'm going to do 1, and that exponent button, -9. And that exponent means times 10 to the minus 9. And so when we do that, now here's where we're not going to be calculators, we're going to be real people. 589, and then notice that it says times 10 to the, it says e-7. We're not going to write e-7. We're actually going to write out what the number actually is, that. Okay, so I don't want to see any of this junk. Okay, that's not the right way to do things. Okay, we use a calculator. That's a calculator abbreviation. It's not an abbreviation that we should see in the class. Okay, so now it's just a matter of plugging in times 10 to the 8th equals whatever the frequency is, we don't know, times 5.89 times 10 to the minus 7. Okay. So now, in order to solve for frequency, we divide both sides by 5.89 times 10 to the minus 7. 5.89 times 10 to the minus 7. Okay, and so now we plug that into our calculator. And again, we're going to use that exponent button. 3e8 divided by 5.89 e-7. Now, always double check that you put it in your calculator correct. Okay? Because 90% of the errors that I see are because people aren't putting it in their calculator correct. And so the answer to this is 5.09 times 10 to the 14th. And then what's the units for frequency? The unit is hertz. And so that's your answer. Okay? Okay, so let's try another one. Oh, this one's multi-part. Okay, so a microwave. We have a microwave that has a wavelength of 0.13 meters. Okay, so we know lambda equals 0.13 meters. Make sure that you put a leading 0 in front of your decimal point. That way there's no confusion about where the decimal point is. Okay, and so we want to determine what the frequency of the wavelength is. So we're going to use, we want to know what nu is. Okay, well that's a question mark. Well, what formula relates of E equals H nu and C equals nu lambda? Which one do we use? Well, it's this one. Okay, so we need C. C equals 3 times 10 to the 8th meters per second. Now, this is really good because this is already in the base unit of meters, so we don't have to convert nanometers or anything to meters. We're already in meters. This is already in meters. Life is good. Okay, so we have the formula. We're going to go C equals nu lambda. We plug in the numbers 3 times 10 to the 8th equals nu frequency times 0.13. Okay, so we go 3e8, again that e times means times 10 to the, divided by 0.13. And so now we get this crazy long number. Okay, so one of the things that I can do is I can change the mode, and I'm going to put that mode in scientific mode. Okay, I'm going to go quit, and now I'm going to recalculate that answer, and look, I get an answer of 2.3 times 10, and notice that it's way over here, okay, times 10 to the 9, and then the unit is hertz, and that equals our frequency. Okay. Now it asks to calculate the energy. Okay. Well, there's only one formula of these formulas that has energy in it, okay? Energy equals E equals h nu, so we need the frequency in order to calculate the energy. Or the formula that you could also use is E equals hc over lambda, which relates energy to wavelength. But I'm going to use this formula right here. This is Planck's formula, okay? And so now I'm going to take this and I'm going to get rid of this information, okay? I'm going to look here, okay? That's it. And now I'm going to go for part B. I'm going to go energy is what we're looking for. E equals question mark. So we need h and we need nu. So h is Planck's constant, 6.626 times 10 to the negative 34 joule times seconds. Okay, totally crazy, but that's what it is. And then frequency, we just figured out, is 2.3 times 10 to the 9th hertz. Okay, so now I'm going to get rid of this. Okay, give me a little room. Joule seconds. Okay, so the formula is E equals h nu, and now we have h. So now we plug and chug. 6.626 times 10 to the negative 34, and that times 2.3 times 10 to the 9th. Okay, so the energy here, okay, and I'm going to use the calculator, 6.626 times 10 to the negative 34 divided by, oh, not divided by, times, okay, times 2.3 times 10 to the 9th. Okay, I have an error. Oh, look at that. Okay, I'm going to call that up and then I'm going to delete that end parenthesis there. Okay, so the answer here is 1.52 times 10 to the minus 24, and the unit for energy is in joules. Okay, you may ask, how does that actually work? Okay, how does that unit actually work? Well, if we take this and we, instead of plugging in the numbers, plug in the units, let's figure that out. So I'm gonna, let's see, I'll do it down here. So E equals h nu. H has a unit of joule times seconds, but then the unit of frequency is hertz, which is also 1 over seconds. So the seconds cancel, leaving us with just joules. So the unit is joules there. And that works anytime you're doing units, is that you should end up with equality there, with an equality. Okay, is that the energy equals joules, that should always then cancel out to give you joules anytime you're calculating energy in chemistry or physics or anything. Okay, so that's the amount of energy that one photon has. Now the question says, well, how many would be in 100 photons? Well, to determine the energy of 100 photons, well, if one photon has this much energy in joules, if I take that number and multiply it by 100, that gives us the energy of 100 photons equals 1.52 times 10 to the negative 22 joules. So you have 100 times greater energy. Well, and then the last one is, what if you have a mole of photons? Well, you have to know how many is in a mole, okay? So a mole of things is 6.02 times 10 to the 23rd things. And so if one photon has 1.52 times 10 to the negative 24 joules, okay, well, in order to figure out how many or how many joules there are in a mole of photons, we're going to multiply that by 6.02 times 10 to the 23rd photons, because that's how many a mole is. That's the mole number. So we're going to go 1.52, again, E negative 24 times 6.02 times 10 to the E 23. Okay? Now just make sure you're watching what I'm doing. Okay? I can't emphasize that enough. Okay? And now this gives you an energy for a mole of photons as 9.2 times 10 to the minus 1 joules, which is a significantly larger number than 1.52 times 10 to the negative 24. Okay, and that's a lot of energy. Okay, so let's do the last problem. Okay, and I know I'll move the calculator a little bit. Long video, but working through these problems will help you immensely in terms of how to manipulate the equations and things. So we have an X-ray. X-ray, high energy. So energy and frequency are directly related. As frequency increases, energy is going to be greater. And so this should be a high frequency. Okay? It says determine the energy of a photon. So just one photon. So we just are going to use E equals h nu, because that's the formula that relates frequency to energy. Okay, and then after that we want to determine the wavelength. Well, okay, so we want to know the energy. We have the frequency. So E, we want the energy. We have the Planck's constant, 626 times 10 to the minus 34 times 3.95 times 10 to the 18. Okay, so 6.626 times 10 to the negative 34. Okay, that number times 3.95 times 10 to the 18. Okay, and when you write this down, you get that the energy is equal to 2.61 times 10 to the minus 15. And the unit of energy, joules. Okay? And that is high energy for one single photon. Okay? And then it says determine the wavelength. Woo! Okay? Woo! Wrong way. So if we're going to determine the wavelength, here's what I'm going to do. I'm actually going to use the other formula, E equals hc over lambda. Okay? Only because I want you to see how that formula works. Okay, so we're looking for lambda. We have energy. What is the energy? 2.6 times 10 to the negative 15. 6.626 times 10 to the negative 34. In order to do this, I may have to get rid of this because this is a pain in the neck. Okay, so let me rewrite that. So we have E equals hc over lambda, so it's 2.6 times 10 to the minus 15 equals Planck's constant, 6.626 times 10 to the minus 34. That times the speed of light. Speed of light is 3 times 10 to the 8th. And all of that is over the wavelength. Now, I'll get rid of this stuff. I've written all this stuff. Okay. And so, in order to solve for this problem now, when you have the value on the bottom that you're trying to find, it becomes a little trickier. So what we're going to have to do is get this on the top. The way to get this on the top is to multiply, and I'll do this in red, multiply both sides by lambda. Okay, and so now lambda cancels here, okay, and now we have lambda times 2.6 times 10 to the minus 15 equals 6.626 times 10 to the minus 34. I don't know why I was writing 5. Times 3 times 10 to the 8th. Okay, and now in order to get lambda alone, we're going to divide both sides by 2.6 times 10 to the minus 15. That cancels out. Divide this by 2.6 times 10 to the minus 15. Okay, so you get 6.626 times 10 to the negative 34 times 3 times 10 to the 8th divided by 2.6 times 10 to the negative 15. Okay, and then you get an answer that the wavelength is, let me write it in black, that lambda equals 3.18 times 10 to the minus 12, and what's the unit for wavelength is in meters. Okay, so there's your answer. Okay, if you try it the other way, you can also get the same answer if you use C equals nu lambda. Okay, divide that. Here, I'll do the same thing. What's the frequency? 3.95 times 10 to the times 10 to the 18th. Okay, and then we're going to take the speed of light, 3 times 10 to the 8th, 3 times 10 to the 8th, and divide that by the frequency that we just had, and we get some value there that's not exactly the same. Oh, I see what I did. I forgot to... Okay, let me... I'm doing this because I want you to see that it's actually, you know, it can be hard to come up with these answers. So I see what my problem is that I deleted this, and so now we get the same value. Okay, 7.6 and 7.6. Okay, so this should be 7.6 times 10 to the minus 11. Okay, sorry about that. Okay, helps if I plug it in right. Some of you may have already seen that and saw it. Okay, so really long video, but I need you to take the time to go through and see how these formulas work and get your hands dirty, and you can get paper dirty to work your way through it. Okay, so have a great time and enjoy.